Yeah, thank you everybody for coming. I'm going to be talking today about my thesis titled Leveraging Information Sharing for Satellite Coordination and Navigation. So the number of satellites orbiting Earth is growing, and it's an exciting time to work in the space industry. These satellites are performing vital tasks ranging from Earth observation to telecommunications to GPS. However, this increase in satellites has a cost, and while space was once thought of as too big to ever have to worry about collisions, times have changed, and satellite operators nowadays receive hundreds of warnings about potential collisions each week. And this is concerning because should a satellite collision occur, sorry for the Zoom overlap for in person, should a collision occur, satellites are orbiting at roughly 7.5 kilometers per second or 16,800 miles per hour. So at a speed like that, when two satellites hit one another, they shatter into thousands of pieces, which can remain in orbit for centuries. This growing number of satellites and the heightened collision risk has made space traffic management an active area of interest in the field. The majority of space traffic management, as I've defined up here, refers to the systems, procedures, and services used to ensure safe and efficient movement of satellites. The majority of current space traffic management procedures require some amount of manual oversight to either make the determination if satellites want to maneuver, sometimes calculating what that maneuver will be, and then uplinking it to the satellite themselves. However, with the number of satellites up there, this manual process doesn't really scale well. So this is where advancements in autonomy would really benefit this field. Advancements in autonomy could create more capable, independent satellites that get to decide on their own whether they're going to maneuver using the information that they have on board. So my thesis has been focused on the development of algorithms and models for autonomous decentralized space traffic management. And what I mean by decentralized here is where responsibility is distributed among the satellites themselves rather than having some sort of centralized oracle that would be directing everyone. So that's the focus of my thesis. Let's go in a little bit more about what current collision avoidance processes look like. So current collision avoidance processes can kind of be broken up into 3 phases. In that first phase, we have ground and space-based telescopes taking constant observations of satellites to inform their understanding of what the satellite's orbit is like. In the second phase, these observations are used to inform the forward propagation, the forward trajectory that the satellite will be at, and they look and see if there's any intersections that there could be a collision in the future. And so on the chance that they actually find a collision, then this third phase is initiated where they issue a warning message called a conjunction data message, or a CDM. And this CDM contains information like the probability they think this collision will happen and the timing of said collision. So to give some insight into how this looks like on a week-to-week basis, as I said before, these observatories are continuously scanning the sky as indicated by that blue bar. At roughly every 8 hours, they use those observations to perform a check to see is there any intersections between all the satellites in orbit and see if there's any potential collisions. If they find a collision, they issue that first warning message, as I said, called a CDM. And so they'll continue on taking more observations, checking to see if this specific collision is going to continue happening, and then continue to issue, hey, this collision is still scheduled to happen. Here's the updated characteristics of it. Now, satellites themselves maneuver independently of this observation scanning process. So sometimes there can be a lag between the maneuver and the observations. So sometimes even though a satellite's moved, there's not been any observations about it since that happened. So they can still kind of get a CDM issued. But future observations will find that the collision has been resolved and no CDMs are sent. So in this example scenario, that particular collision is considered handled. Now I want to go into some case studies so you can kind of get some insight into what current collision avoidance processes are like. I'm so sorry about the elliptical. Oh, don't show it. How about that? Did that work? I can't click it. Okay. Sorry, this is bothering me. There. Okay. So let's go into this first case study. to kind of get a sense of the weaknesses of current systems. So in this case study, we have an elliptical orbit. We have an elliptical orbit here, where the video that should be playing. So a satellite in a highly elliptical orbit with a large covariance. So in this case, this covariance indicates we don't have good certainty of the satellite's exact location. So the current way that collision avoidance procedures are done, they're not just looking for an intersection with that dotted trajectory line, they're also looking for the intersection with that covariance area to be, very precautious. So for a satellite with such a large covariance, sometimes these covariances can really span to be like a 1.5 kilometers, which is quite substantial. You would expect to find very early on, like 7 days out, that a potential collision is ahead. So we'll continue on with that and say we found a collision 7 days away from now. So that means this specific operator is going to get issued a warning as soon as possible and keep getting issued successive warnings about this potential collision. However, it turns out with more time, that due to the propagation abilities of such an uncertain object, it turns out this was a false positive and this collision is actually not going to happen as we get closer to the collision. So this leads us to bad outcome number 1 of the current collision avoidance processes. They kind of have a high rate of false positives, which is harmful because it not only inundates satellite operators with a lot of these warnings, but it also is damaging their overall trust in current processes and whether to take these CDM messages seriously. So this motivates overall like the development of space traffic management services that can actually verify whether or not these CDMs are true with better trajectory information. So in the next case here, we'll say we have a satellite in a circular orbit as shown by the orbit figures to the right. This satellite's very well known. It has that small covariance region as indicated by the shading around the satellite. But recently it maneuvered, and that maneuver actually put it into the path of another satellite as shown by that like purple dotted line. And so even though this was a satellite that was previously very well known, there was no way for anybody else to know that it was going to maneuver. And so unfortunately, this puts it on the chance of collision. So for satellites like this, because that maneuver happened without the observers ever being able to know, the first time they could notify about a collision is only 2 days out, which brings us to like bad outcome number 2 of these current systems. They can, depending on current systems don't have insight into what operators plan to do, which can lead to these really last minute high risk collisions with very little time to react, which is dangerous because, as I said before, we're trying to avoid collisions here. So I've talked a little bit about the weaknesses of the current collision avoidance approach, but now I would like to shift to the benefits of a decentralized autonomous approach to space traffic management. So the first benefit to taking a decentralized approach would be improved space situational awareness. If satellite operators were actually taking a vested interest in their local environment and the overall their local environment, then they would be sharing this high fidelity information and there would just be reduced uncertainty over their precise location. The next benefit would be in collision warning validation. So as I said, they are going to be receiving these tons of CDMs regardless, but a lot of these conjunction data messages could be resolved if you actually had perfect knowledge of where that satellite would be at that time. And that information is available to these individual satellite operators. And the third benefit is in maneuver negotiation. So as you've kind of seen in these ConOps breakdowns, the maneuver process is kind of independent of the observation and characterization of a collision event. But there's a lot of room for improvement in terms of, can we negotiate when maneuvers happen? So if you know one satellite's going to maneuver to reduce the collision, can that maneuver be incorporated into a station?
Yeah, I was gonna say, I think.
Or I think that got muted, sorry. Can that be incorporated into a station keeping event? Or can we consider more nuanced issues of fairness and who has the responsibility to maneuver and try to balance out who's maneuvering if you have repeated collision events with the same satellite operator? So historically, now I want to cover some historic uses of autonomy in these 3 areas. in space situational awareness, a lot of the historical application of autonomy in this domain has been in scheduling telescopes more efficiently using machine learning to get more satellite observations. So the premise behind this is if we can use our telescopes better to get a better idea of where everything else is, then we're reducing the uncertainty around satellites, and then we can provide more accurate warnings. So this GIF I have on the right is actually like above the sky in Cambridge at like 11 yesterday. So that's for like, about a minute or so. So it's actually quite, if you're someone who's operating a telescope and you're thinking, I need to see everything at once, that's not physically possible depending on the characteristics of the telescope. So it's quite a challenging problem. Now, in the area of collision warning validation, existing work in this domain largely looks at using machine learning to forecast collision risk from data from past collisions. So what they do is they take all these historical conjunction data messages and look at their evolution up until collision or up until resolution, and they train off of it and look and see like, okay, typically the probability of collision decreases or increases in this way. So if we're feeding in another similar conjunction data message, what's your estimate for how the probability of collision will improve? And then in this third area of maneuver negotiation, work in this area really looks at finding rule-based metrics for decision-making. So in a lot of other traffic domains, like ships, for example, there's kind of a historical precedent for a rule of the road. When two ships are on a collision course with one another, they'll both turn starboard and they both know that's what the other ship is going to do, and that's how we're successfully going to avoid collision. So these sort of works are looking at how can we implement a similar principle in space. So with the idea being if people's behavior is more predictable, then that's going to make the whole space environment safer. So this brings us to the contributions of this dissertation. My first contribution is producing a model for decentralized autonomous decision-making for a set of satellites for collision avoidance applications. My second contribution is an asynchronous communication limited multi-agent reinforcement learning model for decentralized collision avoidance. And my third contribution is an assessment of non-cooperative collision avoidance strategies using game theory to identify recommended maneuvering strategies. So coincidentally, that also lays out the rest of the talk. So I'm going to go a little bit more into that first contribution. So in selecting a methodology from this work, as I had showed at the very start of this presentation, we wanted a method that was scalable due to the number of satellites in orbit. We also wanted a method that would allow for some level of autonomy, as that manual oversight is really one of the main drawbacks of space traffic management processes now. And then the third thing we looked for in a method was that we think for this specific problem, what really defines it is that the interactions between satellites really shape collision avoidance. So we wanted some method to model dynamic settings where agent interactions shape the problem. So this cross section led us to choose multi-agent reinforcement learning, or MARL. I'm probably going to use those two interchangeably. So what is multi-agent reinforcement learning? Multi-agent reinforcement learning is a type of learning that looks to find a set of desirable behaviors through trial and error of an environment. So in multi-agent reinforcement learning, you start with an agent or a satellite in this case, and this satellite has a state, which we've defined to be its position and velocity. It also has an action set, which we've defined to be that the satellite can move up, down, left, right, or just stay on its current path. Satellites don't get to just stay in place, unfortunately. Once it decides an action to take, this updates it produces an updated set, which, as I said, was a position and velocity. And using this state action pairing, it receives a reward, which is essentially feedback on how well that state action pairing led to whatever behavior we're trying to train from the satellite. So in our model, we define this reward to be a goal reaching reward. So it gets a pretty high positive value when it's actually at a desired rendezvous location, a collision penalty, which is a pretty negative value because that's the whole thing we're trying to avoid, and then a distance to goal penalty, which is essentially a value that's proportionate to how far away the satellite is from its intended location, so we can learn this gradient as it gets closer. So over time, this combination of these three values is teaching it our desired goal-reaching, like navigation, collision avoidance behavior. But as I said, we're working in a multi-agent space, so we make a slight tweak because we're dealing with multiple agents at a time. And so instead of just receiving an individual reward, every satellite actually gets a joint reward in training that is based off of the performance of all 3 satellites. And we're doing this to encourage cooperation. And so what we've found through experimentation is really that with this joint reward, it allows satellites to, if they're only thinking about how fast they can get to the goal, sometimes they can proverbially cut off other satellites that are also path planning. So this really encourages more collaborative behaviors like that. So the multi-agent reinforcement learning algorithm is only one part of the piece, or is only one part of the algorithm, overall algorithm. So Marl gives us, the way to choose actions in this environment, but my contributions really lie in the second piece, which is a graph theoretic method for satellites to communicate and recognize the importance of different pieces of information they're sharing with one another. So altogether, this produces an algorithm we're calling InfoMarl, which is, as I said, not autonomous, decentralized satellite collision avoidance algorithm. So why use graphs? Graph theory is ultimately the study of relationships, and there's a lot of precedence for using graphs in navigation and kind of like social relationship tasks. Graph theory is a lot of the underlying algorithms for Google Maps. There's a lot of graph theory work in social network analysis and DNA sequencing, and so we thought it was well suited to this problem. Now in graph theory, there are 2 different types of information sharing approaches. There's this global information sharing type. And so in this class, satellites are sharing everything with everyone, and they have this perfect knowledge of everybody else in the environment. So you can kind of consider this to be like Professor X, where you have like a almost like essentially telepathic ability to know about everything else that's going on. The second class is this local information sharing class, where satellites are only sharing with a select few. And so this class really resembles more like Mr. Rogers, where they're only getting information when they're being a good neighbor and actually talking and learning through talking. So because we're dealing with, we're interested in scalability and decentralization, we're going to be using this local class, but make comparisons with global to kind of get a difference of our an idea of our performance. So to form the graph in our environment, we start with the satellites, and every satellite becomes a node in our graph, and communications between them become edges. So each node represents a particular spacecraft, and they can encode qualities including the spacecraft's size, its maneuvering capabilities, and its precise location. Edges represent communication and sensing abilities, so they encode qualities including the relative distance between nodes. Could also include things like the areas surveyed if you're thinking more of an observation type mission, and other qualities related to path planning. Our graph formulation is dynamic, meaning that over the course of the simulation, the nodes can communicate, attach and detach. So you get these really unique graph substructures where like at the final step T to the n, you have everyone communicating fully. And also substructures like at step T1, you have this one satellite that's actually not communicating with anyone. So we take the satellite environment, make this graph representation, and then pass it into a graph neural network to learn an encoding essentially of different communications between different nodes. So this encoding, I will save you the math, and we're just going to use that inverted envelope symbol to essentially mean this is the output from the graph neural network. Now, if we stopped here and said we're just training everything decentralized all the way through, we would hit a very common problem with decentralized training where agents get caught in a local minima because they don't learn from the other ones in the environment. So because they're only in that local minima, like for example, this bottom left node would never really learn collision avoidance because it's not near anything. So it could get incorrect behaviors when it actually has a setting where it needs to learn collision avoidance. So the change that we make is that we're training in a centralized manner, and then we're actually deploying in a decentralized manner. So to train in a centralized manner, we provide feedback to the nodes by looking at the whole graph. So we take the complete graph representation, we collect all of the encoded messages and produce an n by n, where this is n satellites, the total number of satellites, an n by n matrice. to represent the full graph communications. But because we're considered about scalability, if we were modeling, 1,000 satellites on 1,000 by 1,000 matrix is just computationally expensive and difficult to manage. So we apply a mean pooling operator, which allows us to produce this compact XAG representation of our graph. And so because we have the same representation for the graph, regardless of the number of agents in the simulation, we're able to take learning from a smaller number of agents and deploy it to larger numbers of agents. So to look at the graph training, or to look at the whole algorithm training process in its totality, we first start at the node level for the satellites. So satellites are first taking their own observations and then communicating with others nearby to build their knowledge of the environment. And then they get an encoded representation of their understanding of the environment, which is used to inform their action. Then the actor network and the reinforcement learning algorithm determines some action for each satellite to take. These actions are applied and the whole graph is updated to see how well the action selection did overall. So we produce that XAG vector. And then that's used to inform the critic network. So if you have the full graph view looking at everything, then the critic network says, okay, well, satellite 1 did pretty good, but satellite 5 did not. So it produces this value feedback to inform future actions. So this process continues iteratively until training is complete. The graph pieces are shown here. The multi-agent reinforcement learning algorithm is shown here. Now I want to shift to how well the training results themselves are. So we heard a little bit about the methodology. Now we're like shifting gears to results. So what we have here for people not in RL is a reward curve. And so as I said at the beginning, our reward function, your positive reward when you get to the goal and you don't have collisions. So higher, like the top right is the utopia point where you want to be. And then the x-axis is the training steps, so how much it's getting trained over time. The dashed lines here represent that global information, represent multi-agent reinforcement learning algorithms that use that global information class. So that means they have that like telepathic ability. Every satellite has perfect knowledge of everything else at all times. And then our algorithm, shown in red in the solid line, is that local class. So what you can take away from our work on this reward curve is that our framework's able to obtain a comparable reward to those that have global information. Now, this work was done in close collaboration with my lovely lab mates, but one of the pieces that I've really taken on is looking into additional learning mechanisms to kind of improve training and robustness to the space domain. So to improve the learning process, one thing I've explored is using transfer learning, which is a type of learning where a model developed on a task is used as a starting point for a model that's for a separate task. So there's a lot of like natural intuition to this learning for how you would explain learning in a normal human setting. If you know how to ski on a mountain, you have a little bit of an advantage if you're going to learn to water ski, but it's not one-to-one. So in transfer learning, you would like to see these 3 benefits for successful deployment of transfer learning. So the first would be a higher initial start. So kind of exactly with that jet ski example, you would expect that a model that's previously there already has some intuition for the skill just from the jump. The next you'd look for is a higher slope, indicating that the learning rate of the model is improved. And the third thing you would look for is a higher asymptote, indicating that the reward convergence by the end of training has improved and it's has more skill with transfer learning than it would have without. So in our work, we're interested in applying transfer learning from other similar multi-agent environments to speed up training and overall improve performance in ours. So more specifically, we're looking at training from simpler ground environments and applying them to multi-satellite space environments that have complex dynamics. So on here, you have that same reward curve that I had shown earlier, where the dashed line is the telepathic one, the solid lines are that local information class, and we see with transfer learning, as shown in purple, we're able to achieve that higher convergence that we're looking for, and also the higher slope, indicating it's learning at a faster rate and also has more skill at the end of the training process. sorry. So all of the models that we've looked at so far have been on this kind of like perfectly spherical Earth, but we wanted to increase the robustness of our models by accounting for additional perturbations from Earth's gravitational field. So now we're looking at models that can deal with, now we're deploying these satellites in a space environment model that has J2 perturbations. So we then use transfer learning in this case, applying from a ground model, like the ground simple method, and then transferring it to this complex perturbed space environment. And we find that transfer learning in this case continues to have those benefits where you once again see, that higher asymptotic convergence, improved learning rate, and then a little bit of benefit at the skill at the start. Something else I wanted to call out in this graph that's kind of more visually apparent than in prior graphs is that you see the info model that's trained from scratch here has a lot of variance in how well it really could learn. So this means you could have instances where you train and it's actually learning very well, and then instances like this bottom part here where it really struggled. So with transfer learning, which you only have to train a little bit, you get this huge performance benefit, and that the stability of this purple line has much smaller variance. So it's providing learning stability and also additional skills. So the results here involve dynamics for this specific inclination, but we wanted to extend our analysis to evaluate multiple inclinations and just test the robustness once again. So we find across a lot of inclinations, you still see that positive asymptotic reward, indicating more converged skill at the end of training through transfer learning. So now to shift to testing results. So everything I've showed so far is for training and learning, but now we're looking to deploy it on algorithms with no more feedback on how well they're doing. How well they do is how well they do. So here we have an example scenario where this satellite representation form is on the left. And so you see satellites here. They're tasked with a rendezvous task where they have a specific star location they need to go to. And we've said, get there and don't collide with anything else. And then on the right, we have the node representation form where that's essentially how it looks in our graph theory model. So in all future GIF type things, we're going to be showing the node representation form, but keep in mind that the node represents a specific satellite. So you see here that for this example scenario, we're doing the thing. We have successful satellite navigation without collision, but then we wanted to look past one single scenario. So we looked at across 100 cases across different seeds, and we found when you compare with other standard multi-agent reinforcement learning algorithms, both global and local, ours has a very high success rate for this domain, outperforming those that have more information, which is really exciting. Next, to really look at the scalability of our algorithm. So as I said before, the xag vector, that pooling operator, allows us to transfer learning from smaller numbers of agents to larger numbers of agents, but that just essentially means that the matrix math will check out. It doesn't always necessarily mean the scalability will apply. So I want to call attention to another feature of our algorithm, which is its permutation invariance. So when a satellite, as I said here, is a node, when a satellite's communicating, it has node permutation invariance, meaning that this graph representation on the left is equal to this graph representation on the right. And we think this is really key to the overall learning of this algorithm, because it allows the algorithm to have a better understanding of the importance of different proximities between satellites, rather than overfitting to, oh, I always know the satellite's to the left of me, and this is how I behave to a specific satellite, and more I'm learning when I'm in proximity and in these formations, this is how I navigate around them. So each of these were trained on 3 agents, and then we're testing it, on 3, 9, and the right kind of looks like an evil crab, but that's 20. We also look at the generalizability across tasks. So here we've challenged them to form a line independently, that figure 8 shape, and then finally an M shape. So we see that, in more complex formation flying tasks, it's able to, handle them. Okay. Now I want to wrap up these results here with what I think is one of the most powerful components of our framework, which is its ability to quantify the impact of different pieces of information. So what we've done here is test the impact of goal sharing versus not goal sharing. So on the left side, agents that aren't sharing their goal are not sharing this green star. They're only going to share their current position and velocity when they're within a sensing range of another satellite. And then on the right side, they will be sharing that forward-looking information. So we find that models that only are sharing their current location perform worse, like they have more collisions than models that are actually sharing it. We also really went into the minutia of what exactly is leading these goal sharing models to perform better. And we're finding that overall, they just have more efficient path planning, like reduced collision numbers at the end of the episode. On the chance that they didn't have enough time to get to the goal, they're much closer and probably would have gotten there if we allowed the simulation to run longer. But all this comes at in a cost of increased fuel usage. So to have a quick section wrap up of this contribution, I created a model for decentralized decision-making for satellite collision avoidance. I've demonstrated that this methodology performs comparable to others that have access to more information. And I've also demonstrated the effectiveness as transfer learning to really improve learning in this setting. And we've also used this graph formulation to really look at the value of forward-looking information, such as maneuver sharing, and shown that it leads to improvements in path planning and overall reduced collisions. So now to shift to the next main contribution of my thesis, which is an asynchronous and communication limited multi-agent reinforcement learning algorithm. So in the work that I've talked about so far, all of the satellites involved are communicating synchronously, instantaneously, and frequently. But unfortunately, this leads to a lot of communication overhead. So we've explored an extension of this first work, which we're calling asynchomorph, that still has that same, graph theoretic multi-agent reinforcement learning formulation, but we're looking to reduce the overall number of communications it takes and also allow for agents to take actions at different periods. So I want to go over some key features that differentiate it from InfoMorph. The first is that we changed the graph structure to be more temporal. So satellites are only communicating when they're acting at the same time, and they can also sense each other. They're not just communicating because they're close enough and they can talk. So this little animation here, these two are the only ones that communicate because they're making a decision at the same time. The next feature we have is a more sparse reward. We found that upon experimentation, that joint reward function I had mentioned earlier, where all three agents and trainings share the rewards with each other, like they share a summative reward. If an agent is at its goal, it kept on getting that positive reward, which could really obscure, this other agent trying to make more minutia path planning changes. So we've adapted the reward structure to be more sparse, so it's a one-time goal reaching reward. And then finally, this third feature, we've implemented a squeeze buffer in the replay trajectory. And so what that does is only when agents are actively taking actions are those actions stored in the replay buffer. It's not the same as having an action stored at every time step, which is the way it was before. So we have a motivating experiment here looking at this asynchronous communication limited setting. And we find that asynchomorph, our algorithm, uses a fraction of the communication that InfoMorph has. It's adapting to asynchronous communication. It's successfully goal reaching, as evidenced by this number, and it's overall communicating less frequently. Then we looked at the performance against comparable algorithms. So these are other multi-agent reinforcement learning algorithms that are looking to have minimal communication. And we find that our framework has one of the strongest performances in this area, outperforming comparable methods that are seeking to minimally communicate, that are either seeking to minimally communicate or allow asynchronous coordination. So to wrap up this section here, as I've said, I've created a model for asynchronous decision-making for satellite collision avoidance. I've demonstrated the performance of this methodology, and then this is more of my thesis but I've provided empirical comparisons of the impact of different attention mechanisms on resultant coordination abilities. So we're in the home stretch. The final contribution of my thesis is game theoretic models for non-cooperative interaction between satellites. So in the methodology I've discussed so far, I've really been leaning on multi-agent reinforcement techniques. And so multi-agent reinforcement learning and game theory have a lot of overlap between each other in fields. I'm sure like theorists in each would say they have the perfect solution that could be applied in either technique, but we really use multi-agent reinforcement learning for prior work because we believe its best strengths are best demonstrated in problems that are partially observable, where you have a dynamic changing environment, where the interactions of the agents really shape the problem itself. We're shifting to a game theory approach in this last contribution because it provides a mathematical formulation for strategic interaction and allows you to define a game with specific rules. So it really allows us to examine different trade-offs between satellite operators. And so we view the non-cooperative satellite collision avoidance case to be really similar to a problem in game theory known as the game of chicken, as exhibited by this clip from Fast and Furious 7. So the game of chicken is one where you have two cars, in this case, on a head-on path. And if no one moves, they crash, as shown. So that's the worst penalty. But if you're the one to move, you are humiliated and considered a chicken. So we think that this famous problem in game theory shares a lot with the non-cooperative collision avoidance problem, as you obviously don't want to incur this severe penalty of full-time collision, but you also ideally would like to avoid maneuvering. So in our game theoretic setup, we start and define a satellite with these three characteristics. We define them to have some sort of risk tolerance. We define them to have some sort of cost to risk losing the satellite. And we define them to have some sort of fuel cost to maneuver. And so we have two players here, each with their own value for these three characteristics. And then we're going to go and fill out something called a payoff matrix, which is something in game theory used to kind of visualize the outcomes of different strategies. So we can go through and fill this table together. So for satellite one, if satellite one is to move, the only real penalty to moving is that fuel cost to maneuver. That's the most painful part of that interaction. And so we fill out those two in this row. And then similarly, satellite two, if satellite two is to move, then that once again is really only incurring that fuel cost. So for this top left and bottom right quadrant, these are move weight strategies. So that means one of the satellites has moved, so the collision is considered resolved. So there's no real penalty to the other one. So we fill out a 0 to the opposing satellite. Now this weight case in the non-cooperative collision avoidance problem is a little bit more tricky than what happened in Fast and Furious. In Fast and Furious, we knew for a fact they were going to hit each other. That was not why you were shocked and astounded by that clip. In the satellite collision avoidance problem, there's a lot of uncertainty over where satellites actually are. So I want to spend some time kind of talking about probability of collision and how we really modeled the penalty to both of them weighting. So probability of collision in the, to calculate probability of collision for satellites, you start with an example satellite case as shown here. You take the covariances of both satellites and combine them to make a slightly bigger one. So this is a cautious estimate of the maximum uncertainty of everything involved. Then you want to have a cautious estimate of the largest area those two could intersect. So we make a circumscribing sphere for if both of them are right next to each other. This is for putting a sphere approximation to say this is the maximum area they could have. And then we take this sphere in this huge uncertainty region and we integrate over it and produce the probability of collision. And so I'll once again save the math, but to kind of give a sense of the type of numbers you would expect to see and the concern it would elicit from satellite operators. Probability of collision of 1 in 10,000 is considered really, really concerning and worthy of moving immediately, which is a 1 in 10,000 or a 1 in 1,000 risk in day-to-day life would be a non-issue, but for satellite collision avoidance, that's very severe. 1 in a million risk is kind of on the borderline of acceptable. This is the threshold used by SpaceX. If they have a CDM at a certain point in time, usually like 48 hours out, if it's still a 1 in a million chance, they will actually initiate a maneuver. And then you have a 1 in a billion chance, and even for satellite operators, that's considered like a non-issue. So you're working in this very interesting domain where you have this high severity issue of collision avoidance. It's not just collision as you would see cars on the street. Like if a collision occurs, this is desecration of a public good. Like this would be, some ways like you losing Yosemite, and you can think of that. Like that is a very serious consequence. But you also have these low probabilities that are not like intuitively easy to really wrap your mind around when you're thinking about risk. So for the weight case, what we've ended up doing is we say, if you have an individual risk tolerance, if the probability of collision, if nobody moves, is beneath that risk tolerance, as in it's less likely, then you'll get away with the 0. But if it's more likely, you'll incur this huge penalty. So to kind of evaluate what we've seen as the emergent maneuver strategies for these 3 characteristics, I have this like three axes, and we're looking down on the satellite loss cost and the fuel costs. We're looking down and only looking at the relationship between those two. And so we looked at different values between satellite 1 and satellite 2 for these 2 cost variables. The blue triangles represent weighting, the orange circles represent moving. And you can see it's quite a Rorschach test. There's not really a clear correlation between fuel cost and satellite loss cost for the emergent maneuver strategy. Then when we look on that right pane, we're only looking at the relationship between risk tolerance and fuel cost. We find that there's actually a much easier way to kind of delineate strategies. And so that red line here is the probability of collision if no one maneuvers. So the probability of collision at the time the game is set. And so that really indicates whether or not satellites will maneuver or not, because if they have a risk threshold, for example, of 1 in 10, and the probability of collision, if they wait it out, is 1 in a million, then they're just going to wait it out. That's the way it goes. So this is in the short term. We looked, and then also when you're thinking about long-term costs, like even if we really jacked up the satellite loss cost to be really severe, you still see this kind of delineation of the probability of collision for weight kind of dictates the maneuver strategy. So to wrap up this section and its contributions, I've created a model for non-cooperative collision avoidance, examining trade-offs between maneuver cost, probability of collision, and total satellite loss, and perform some comparisons of different operator characteristics on resultant maneuver strategies. So I want to wrap up this presentation here, kind of talking about what are the implications for satellite operators from this work? How can my work be useful to industry or other academics? So this first piece on decentralized MARL for information sharing and for collision avoidance. And so the value of this work is that it's a proof of concept for MARL in many ways, which is really exciting for the technique. But for satellite operators, this is a really valuable work saying that like decentralized collaboration is possible in this setting, like it is possible in this setting, and also that it has benefits beyond formal collision avoidance, as we kind of exhibited with those path planning characteristics. The next implication in the asynchronous and communication limited MARL section, one of the main takeaways from that is that communication for communication's sake is not necessarily beneficial. Like just because you have the means to communicate frequently and often, we're observing that you really like the collaborative abilities, the navigation abilities of the satellites were not impacted when we reduced the amount of communication. It's really about using it impactfully and really understanding the relationships between the satellites involved. And then in this third piece, the game theoretic formulation, we've found that like individual risk tolerance is really the biggest delineator for how satellites will maneuver. So kind of work conceptualizing how risk works in this, very unique, as I said, like high severity, like low risk domain, will be useful to kind of sussing out what operator behavior would look like for these non-cooperative cases. So altogether, that's my contributions for this dissertation. I'd also like to go through some acknowledgements, if that would be ideal. We're good on time still. I was told these are not graded, and also as long as I could be. So I heard that second part. So first, I would like to thank my